This is the second section of chapter 4, kinematics, and in this section we're going to be looking at acceleration varying with displacement. Now what we mean by that is that to find the acceleration, it's some function of the displacement x. In all the questions that we've done before, the acceleration has been a function of time. So as time varies, the acceleration varies. But here, the acceleration is dependent on the displacement. So it may be that as an object moves closer to the origin, its acceleration may increase or decrease. It's going to be some sort of function of the displacement. So we want to derive an expression that we can use for these types of questions. So let's write down what we already know. Well, we know that we can get acceleration by differentiating the velocity with respect to time. We know that we can get the acceleration by differentiating twice the displacement with respect to time. We know that the velocity is dx dt, and using this a equals a function of x, we're now going to derive an expression. So the first thing we're going to do is to start by saying, right, the acceleration using the chain rule is equal to dv dx times by dx dt. So I've been using the chain rule here to get that, and if you think about it, if you multiply these two fractions out, the dx's will cancel out and you'll get dv dt. So basically we've just used the chain rule on this part here. Yeah. Now the second part of our expression, the dx dt, this part here, is v, isn't it? Yeah, dx dt is v. So we can rewrite this expression and say that the acceleration is equal to v dv dx. So just substituting the dx dt, which is velocity, with v. Now we're going to do like a little bit of side working over here, and let's do that in green. And what we're going to do, we're going to see what happens when we differentiate half v squared with respect to x. We want to differentiate that expression. And we're going to be doing this because this is going to be useful for the rest of our working over here. Right, so if I differentiate half v squared with respect to x, well, I differentiate the v as if it were an x term, so that then half v squared just becomes v. And what have I done? I've just differentiated a v term as if it were an x term, because I'm differentiating with respect to x. Now if you look at what we've got over here, v dv dx, that's this expression over here. So now we can replace the v dv dx with d dx half v squared. And we said right at the start that a is a function of x, so now we can replace a and write it down as f of x, a function of x, is equal to d dx half v squared. Now this expression here is the one that we're really interested in. So now we can take our function of x and set it equal to d dx of half v squared. And when we do that, the next part of our working would be to integrate both sides with respect to x. So you'll have the integral of f of x dx equals, now we'll have the integral of d dx half v squared with respect to x. And because we're integrating and differentiating, they're going to cancel out. You can sort of see it, that the dx's will cancel out and the d will cancel out with the integral, leaving us with this statement. And this is going to be very useful. We can now say, right, if I integrate what the function of x is, of the acceleration, that is going to be equal to half v squared. So we want to start with this statement here, set our function of x, the acceleration, equal to d dx half v squared, then the next step is going to be to integrate both sides. Example 7. A particle P is moving on the x-axis in the direction of x increasing. When the displacement of P from the origin, O, is x meters and its speed is v meters per second, the acceleration of P is 2 meters per second squared. When P is at O, its speed is 6 meters per second. Find v in terms of x. Okay, so I've set out this information on a diagram here, and this will just help make sure that I get the signs correct, because sometimes the acceleration is going in the opposite direction. That needs to be a negative, but I can see when P is at the origin, its velocity is 6, that's just marked there. When it's at a distance of x from the origin, it's got velocity v and acceleration 2x. So the first thing I do is to say that f of x is equal to d dx half v squared. So f of x, that's what the acceleration is. It's a function of x, that's 2x. So I'll put 2x is equal to d dx half v squared. Then I'm going to integrate both sides with respect to x. I'll stick a dx there and a dx there. Then what happens, we know that on the right hand side the integration cancels out with the differentiation, so we're integrating 2x with respect to x equals half v squared. Integrating the left hand side, we'll get x squared plus c, our constant of integration, is equal to half v squared. Now we want to find our constant of integration, and we can use this bit of information here, and that is that when x is 0, v is 6, so we'll just substitute those in. When x is 0, so 0 squared plus c is equal to half times by 6 squared. That will mean that c is equal to half of 36, which is 18. So my full expression is going to be x squared plus 18 is equal to half v squared. Now we just need to rearrange it because it says find v in terms of x. So we want to write v equals, so we're going to times both sides by 2, so we get 2x squared plus 36, and then square root it. Now normally when you square root you would consider the positive and negative square roots, but it does say that it's moving in the direction of x increasing, so it's always going to be moving this way. It's never going to be moving in the direction of decreasing x, so we just need the positive square root, but just be aware of that. Always scan the question and look out to see whether you need to put the negative square root as well. Example 8. A particle P is moving along a straight line. The acceleration of P when it has displacement x meters from a fixed point O on the line and velocity v meters per second is of magnitude 4 meters per second squared and is directed toward O. At x equals 0, v equals 20. Find the values of x for which P is instantaneously at rest. So the first thing we're going to do is to put this information on a diagram. So here's my x-axis here, and this is the origin, and we know at the origin when x equals 0, v equals 20, so I'll just mark that down, 20. Then I want to mark the particle P, so there's my particle P, and we're told that when it has a displacement of x, its velocity is v and its acceleration is 4x, but it's directed towards the origin, so it needs to be pointing this way, and we'll put 4x. So the first thing we need to know is that the acceleration is going to be negative 4x because it fits direction. Direction is important. Then we can write down our expression, which is f of x is equal to d dx half v squared. We can substitute in f of x, which is minus 4x, is d dx half v squared. Now we'll integrate both sides, so I'll have the integral of minus 4x dx. The other side just then becomes half v squared. Integrating negative 4 is going to give me negative 2x squared plus my constant of integration is equal to half v squared. How do I find my constant of integration? Well, I use the fact that when x is 0, v is 20. We'll substitute those in. So that would be negative 2 times by 0 squared plus c is equal to half times by 20 squared. 20 squared is 400. Half of 400 is 200. The other side is 0 apart from c, so c is 200. So my full expression for the velocity, and if I flip it around, I've put half v squared, is equal to minus 2x squared plus 200. I can multiply all by 2 and get v squared is equal to negative 4x squared plus 400. So now I can use this expression here to find out when p is instantaneously at rest. So something's instantaneously at rest when the velocity is 0. So I'll just put at rest when v equals 0. So we just set v equal to 0. So I'll have negative 4x squared plus 400 is equal to 0. So 4x squared is equal to 400. X squared is equal to 100. So that will mean that x is equal to 10 and x is equal to negative 10. And that's what we want. We want the values of x when v is 0, and we've worked that out here. When x, the displacement from the origin is 10, so it's when it's 10 meters away in the positive x direction, and when it's 10 meters away in the negative x direction. That's when it's at rest. So I'm guessing it's maybe oscillating, maybe between these points, maybe something like that. Or maybe not, since the acceleration is always toward O in the negative direction here. Could be, I'm not sure. Example 9. A particle P is moving along the positive x-axis in the direction of x increasing. When OP equals x meters, the velocity of P is v meters per second, and the acceleration of P is 54 over x cubed minus 18 over x to the power 5 meters per second squared, where x is greater than or equal to 1. Given that v equals 0 at x equals 1, find v in terms of x. So as always, I start with a diagram here. When x is 1, the velocity is 6. When the displacement of p is x, or when it's at the position x, its velocity is v, and the acceleration is that expression there. So we'll start by saying, well, the acceleration is this f of x, which is 54 over x cubed minus 18 over x to the power 5. I'll just write that again. We'll use our expression f of x is equal to d dx half v squared, half v squared. We'll substitute in and then we'll integrate. So f of x is going to be this, let's do it down here, 54 over x cubed minus 18 over x to the power 5 is equal to d dx half v squared. We'll integrate both sides, so we're going to be integrating 54 over x cubed. Actually, let's write that as 54 x to the minus 3 minus 18 x to the minus 5 dx is equal to half v squared. Right, so let's integrate. So on the left hand side, 54x to the minus 3, add 1 to the power, so it becomes minus 2, divide by minus 2, so 54 becomes minus 27, x to the minus 2, and then add 1 to the power, becomes minus 4, and then we've got negative 18 divided by negative 4, which is plus 4.5 or plus 4.5 or plus 9 over 2, right, it's 9 over 2 x to the minus 4 plus our constant of integration is half v squared. Now, how do we find our constant of integration? As usual, we put in the conditions we're given, that when x is 1, v is equal to 6. Those are going to get substituted in. Now, I'm going to write these and take the things to the bottom. It's just easier to work out than negative powers. So I've got negative 27 over 1 squared plus 9 over, and I'm going to have 2 down here, I'll write it like that, 9 over 2, and times by 1 to the power 4, so it's just going to be 1, plus c is equal to half times v, which is 6 squared. So now we can find c. If we work out the left hand side there, that basically becomes minus 27 plus actually let's rearrange it so we can write what c is equal to. So put c is equal to half of 6 squared, so that's 18, and then plus the 27 over 1 squared, and then minus the 9 over 2 times 1 to the power 4, which is just 9 over 2. So we'll work that out, and c is 81 over 2. So my full expression for the velocity is going to be half v squared is equal to, and I'll write it as negative 27 over x squared plus 9 over 2 x to the power 4 plus c, which is 81 over 2. There we go. So that will be our full expression for our velocity. We can then times both sides by 2, I guess, and also square root it as well. So if we do that, we'll end up with v. So I'm going to basically times it by 2 and put these bits together. It'll be equal to the square root of, and we'll decide in a minute whether we need the plus, the negative square root of this. So this times by 2 is going to be negative 54 over x squared. This one times by 2 is just going to be 9 over x to the power 4 plus 9 over x to the power 4, and then the 81 over 2 times by 2 is just going to be 81. Now, do we need a negative square root? No, because it says here that it's moving in the direction of x increasing. So it's always moving in an increasing x direction, which means that its velocity is always positive. So we don't need the negative square root on this particular question. Example 10. A particle P is moving along the x-axis. Initially P is at the origin O and is moving with velocity 1 meter per second in the direction of x increasing. At time t seconds, P is x meters from O, has velocity v meters per second, and acceleration of magnitude half e to the minus x meters squared, or meters per second squared, directed towards the origin. So let's start first of all with our diagram. So here's my diagram here. Initially the velocity is 1 in the direction of x increasing. When P has a displacement of x, when it's x meters from the origin, so I'll just mark down that this is the origin here, its velocity is v, and its acceleration directed towards the origin is this half e to the power minus x. So part A, find v in terms of x. So we have our acceleration, which is going to be negative half e to the minus x, because you can see it's directed towards the origin, so direction matters. We'll then write out our expression, which is f of x is equal to d dx half v squared. Then from here we'll actually substitute everything in, so we'll now have negative half e to the minus x is equal to d dx half v squared. We'll now integrate both sides. So we've got, let's stick to negative a half on the other side in the integral. E to the minus x dx is equal to half v squared. Now we'll integrate it. Now e to the negative x integrated is going to be negative e to the negative x, so that minus a half becomes plus a half e to the minus x plus our constant of integration is equal to half v squared. How do we work out constant of integration? Let's use the fact that when x is 0, v is 1, so they're going to get substituted in. So that will give us half e to the power of negative 0. Now be careful, negative 0 power to e is not 0, it's 1. That's a common error to do. Be careful, that is equal to half times by 1 squared. That should be easy enough to work out. So you've basically got half plus c equals a half, so c is equal to 0. So our full expression for v, or half v squared is going to be equal to half e to the minus x, and there's no plus c, so let's times both sides by 2, and actually if we do that, that just means that the halves cancel out. We square root both sides. Do we need a negative square root? No, because it says it's moving in the direction of x increasing, so the velocity is always positive. So that means that v is equal to the square root of e to the minus x. Or you could say, right, this is the same as power half. So if I put the two powers together, another way of writing this is e to the power of x over 2, because you're going to do that power x times by half to give you that. Either one of those is acceptable. Now move on to part B. Now part B asks us to find x in terms of t. Now here we'll just use the fact that v is dx dt. So I can take my part A answer, and instead of writing it as v equals, I can write it as dx dt is equal to e to the minus x over 2. Now you may not recognize this, but this is actually a first order differential equation which we can solve very simply by the separation of variables, which you'll find in Pure 2. And maybe if I can work out how to, I'll put a link up into the top corner to that video where you do separation of variables. So separation of variables just basically means like collecting like terms. So we're going to put all the dx terms on one side and the dt terms on the other side. So I'm going to multiply both sides by dt, so dt will come over here. I want the x term over on the left hand side, so I'm going to divide both sides by this term here, which means that this power is going to become positive. So I end up with e to the minus x, sorry, not, I just said positive and I'll write down negative, e to the x over 2 dx is equal basically to 1 dt. Then we integrate both sides, so I can stick an integration sign on both sides like that. That's the separation of variables. We can use the reverse chain rule to integrate this. So when we divide by the inside differentiate is a half. We're going to divide by a half, which is like times in by 2. So I'll have 2e to the power x over 2 is equal to the other side. When you integrate that, it's just going to become t, and then we have a constant of integration. Now when we have this separation of variables, we don't write a constant of integration on both sides, we just do 1, because two constants together just makes a single constant like this. Now I'll just clear up some space up here to carry on the rest of B. So let's do like a big line like this to show that it carries on up here. Now I've used the same letter again as I did in part A. Strictly speaking, we should use different letters because this is a different constant to this one. So yeah, I suppose it's better practice to use like a different letter So I will do that because I don't want to confuse anybody. So let's call this D, or any other capital letter is what we tend to do. How are we going to find this constant of integration? Well, the information that was given us in the question about when it's at the origin, the velocity is 1, and it's at the origin, actually initially at the origin, so we don't need a velocity part. We just want initially t equals 0, x equals 0. So x equals 0 at t is equal to 0. We'll substitute those in. So I'll have 2e to the power 0 over 2. So remember, that's going to be 1, e to the power 0 is 1, is equal to t, which is 0, plus d. So we've basically got 2 is equal to 0 plus d, which gives us d equal to 2. So our full expression for our displacement is 2 e to the x over 2 is equal to t plus 2. Now we want x in terms of t, so the rest of this is just rearranging it to make x the subject. So we'll divide both sides by 2, so we've got e to the x over 2 is equal to t over 2 plus 1. We'll do the natural log of both sides, so that will leave us with x over 2 is equal to the natural log of t over 2 plus 1. Now I put modulus, but it's always going to be positive because t is always going to be positive. And then lastly, times both sides by 2, and we will have x is equal to 2 natural log t over 2 plus 1. So there's our expression for the displacement. So can you see what we did here? To find an expression for the displacement, we took our expression for the velocity and we replaced v with dx dt, and then it's going to be some sort of integration method then to get your x and then make x the subject. Example 11. A particle P is moving along the positive x-axis. At OP equals x meters, the velocity of P is v meters per second and the acceleration of P is k over 2x plus 3 all squared, where k is a constant, directed away from O. At x equals 1, v equals 10, and at x equals 6, v equals the square root of 120. So diagram time. Right, so here's my diagram, all the information that's here transferred onto this diagram here. Now I've put 1 here and 6 here simply because of space. That doesn't mean it's either side of P, just I didn't have enough space to do it there. And actually it doesn't really matter where it is because x is just some arbitrary point along the x-axis. So in part A, first thing we need to do is to find the value of k. Now let's write down our acceleration, which is k over 2x plus 3 all squared. Now it's directed away from O, so it's going to be positive. Then we have f of x is equal to d dx half v squared. We'll substitute in our information. So f of x is k over 2x plus 3 all squared, and that's equal to d dx half v squared. So we integrate both sides, so we're going to be integrating k over 2x plus 3 all squared dx is equal to half v squared. Now if I write the 2x plus 3 squared and bring it to the top, I can use the reverse chain rule because the inside of the bracket here is linear. Again, this is from Pure 2. I'll try and put a link at the top to the video that will show you how to do that. So we'll have this and then half v squared. So the reverse chain rule tells us that we are going to integrate the outside So when we integrate the outside, we add 1 to the power and divide by that new power. Almost forgot what we need to do there. So the power is going to become -1, and I'm going to be dividing by -1. So let's just put a negative in front of that k. The inside of the bracket doesn't change. And then we divide by the inside differentiated, so we need to divide by 2. So I'll just write this here as -k/2. And that's going to equal half v squared. So now we want to find what, we need to put in our constant of integration. So let's call this c is equal to half v squared. And I've been given 2 sets of information, and I need to plug in both because I've got 2 unknowns, the constant of integration and k. So if we start by substituting in the x equals 1 and the v equals 10, what we'll have is -k/2 times by 2 times 1 plus 3 to the power -1 plus c is equal to half times by 10 squared. So if we work that out, this is going to be 5 in the bracket, to the power -1 is a fifth. So if we multiply a fifth by -k/2, it becomes -k/10 plus c, and then half of 10 squared is going to be 50. So that's my first equation. Let's just put a circle around that. You can see the 2 unknowns. So now I substitute in the other 2 values that I've been given, which are the 6 and the root 120. So x equals 6, v equals the square root of 120. So now we're going to get -k/2, and then it's going to be 2 times by x, 6, plus 3 to the power -1 plus c is equal to half times by the square root of 120 squared. So working this out, so we've got 2 times 6, which is 12, plus 3 is 15, to the power -1 is 1/15, times that by the -k/2 will give you -k/30 plus c, and then the square root of 120 squared is 120, and half 120 is 60. So this is now my second simultaneous equation. Now these 2 equations are easy enough to solve because you can eliminate the c by subtracting one from the other or using your calculator. I've been pretty lazy and I used my calculator, and I got a value of k equal to 150. So there we go, that's the value of k. And incidentally, I've got a value for my constant of 65. Moving on to part B. Part B says show that the speed of p cannot exceed root 130. So for this bit I am going to need my constant of integration, so I'll just write it down here. That's the value that I got, and then we'll write down the full expression that we have for the velocity. So we flip it around, half v squared is equal to, let's put the 65 first. So 65, that was my value of c, so that's coming from here, and then minus k, which is 150. So 150 over 2 is 75, so minus 75, and I'll write the -1 part at the bottom, 2x plus 3. So all of that should basically just come from here, substituting in my value of k, 150, 150 divided by 2, 75, and my value of c, 65 here. We'll then times both sides by 2, and that will give us v squared is equal to 65 times by 2 is 130, and then we times the second fraction by 2, so that's going to be 150 over 2x plus 3. Now you can see from this expression that you're actually subtracting something away from 130, and since x is positive, this part of the expression is always going to be positive, always positive. And we know that because it says it's moving along the positive x-axis. So since x is always going to be positive, that means that this part of the expression, 150 over 2x3, is always going to be greater than 0. If we're always taking something greater than 0 away from 130, that means that 3 squared, or v squared, sorry, is going to be always less than 130, which then means that v is always going to be less than the square root of 130 as required. So we've proved that as they want. Yeah, you can see that from expression. It's getting smaller than 130 because this x is positive, because it tells us here that it's positive. So you should now be able to do exercise 4b on pages 159 to 160 of the textbook.